Okay, period five. Like I said, we're going to introduce the concept of quantum mechanics. Try to make this as easy as possible because there's a lot of heavy weight to this brand of physics, but we're not going to do all that stuff like normalization, finding coefficients, and all kinds of nice things, perturbations in energy states, looking at the infinite square well, or quantum tunneling. There's a lot of nice stuff we can talk about, but you're really going to need the math to really appreciate it. And we'll get that on the next level. Go to college and study nice things like uh, ordinary differential equations, partial differential equations, linear algebra. In my humble opinion, become a master at linear algebra, and you'd be on your way to master quantum mechanics. Okay, so we're going to start off with the concept of eigenvalue, operators, and eigenfunctions. Well, I'm just going to introduce them right now as value, operator, and function, but we are going to talk about the difference between a value and an eigenvalue, and a function and an eigenfunction. Say we have an equation up top, y equals x. Well, if y equals 4 and x equals 2, you know that that's not equal. That's an inequality. But there's something that we can do on the function x. Let's call it a function. We know it's a variable, it doesn't do anything. But for our purposes, we'll see what that means down the line. We need to do a particular operation on x to get 4. So we can multiply x by 2, our coefficient, which in this case, in this context, we'll call an operator. This operator, well, operates on x, which is equal to 2 to make 4. So now that's equal, an equality. You have a particular value, say state. We have a state function operated on to produce a state value. I'll just tell you right now, as I'm, waxing nostalgic and explaining things, that an eigenvalue, an eigenfunction, those are only produced from waves. So basically, if you have a wave that's a superposition, it's a collection of all possible values. You can have, let's say that you're dealing with a wave and its energy. Like you can have up to 100 different types of energy for that particular wave. It holds all of those energies at once. When you do an operation called normalization, which we won't do in this introduction, when you normalize a wave function based on a particular operator, you're going to get a particular eigenvalue. Eigen, which we'll see here in a minute, means own or discrete or distinct, particular. It's its own function to produce its own value. Because out of a superposition of 100, 200, near infinite values, we want to do something to that wave function, collapse it such that we produce one result, maybe another result another time. And then based on what we do to that wave function, the mathematical operation that we perform on that wave function is what we call the observable, or the value that we see. Mathematically, that would be the coefficient, which is also the coefficient, or the normalization of those coefficients will produce a particular value. I'm not going to get into all that because it's semantics and things that will throw us over the edge. So, but right now, I just want to introduce and get you comfortable with this concept of value, operator, and function. All right, so let's scroll on down. So, such is the basis for quantum mechanics. Quantum means very small or discrete, distinct, discrete. We call it discrete mechanics, quantum mechanics. It's, we're dealing with little quanta, the photon, the electron. And once we get on that level, several experiments have shown, at least from experiments done by Thomas Young in the 1800s, Louis de Broglie was one quantum physicist that showed that a particle could act as itself a particle and a wave, and that was the basis for his, I think it's 1924 PhD thesis, where he showed that the wave particle duality of everything. Everything is basically made out of waves if you want to take it to that degree. But when we get to the realm of quantum mechanics, we're dealing with smaller particles that give us a particular set of values, because we can't really deal with like large objects like tables in terms of quantum mechanics. Obviously, we're going to deal with those in terms of classical mechanics, so the mechanics that we've seen this year. For quantum mechanics, we usually deal with the hydrogen atom, electrons, photons, very small particles that exhibit very particular waveforms, wave states, same thing. So this idea of value, operator, and function is the basis for quantum mechanics. We constantly deal with operators on some function to produce a value. So in order to get a particular value, which is an eigenvalue, which you see here, we have to operate on a particular function, the eigenfunction, to get that particular eigenvalue. So I was just mentioning a wave function. We're going to be seeing wave functions denoted by the letter psi, the Greek letter psi. You can always think of this wave function as a superposition of all different possible values. It is made up of everything, this psi function. So you can think of it psi 1 plus psi 2 plus da, 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 da. It's a superposition. That's what we mean by superposition. We're adding all of the different possibilities, and then that make up psi. But there is a particular mathematical way to get one of those possibilities. Because in classical physics, we've seen so far, okay, I have a mass, 2 kilograms, and it's moving at 2 meters per second. I want to find its kinetic energy. Bam. I don't have to worry about collapsing wave functions. I don't have to worry about, is there going to be an infinite number of values from there? No, it's only one velocity, one mass, I get one energy. But again, the mass in that situation would be the operator, the velocity would be the function, and the kinetic energy would be the value. But it's not so easy, or it's not so static with the wave function. The waves, can have different states at any given time. It really doesn't matter. A wave does not just have a particular form. It can have a series of forms. Hence, that's why we have a superposition of different wave states, psi 1, psi 2, all the way up to however many that you can have. And when you have an object moving at 2 meters per second, it's only moving at 2 meters per second. Not unless you change it and everything, but is it also simultaneously moving at 3.5 or is it 2? No, it's always 2. But a wave is not always one value. It's a collection. That's what makes quantum mechanics so weird. And but if you get your framework down, like I'm introducing to you, if you get your framework down, then you know how to deal with this weird wave-like stuff. Waves are funky. You throw a rock in the pond, it's going all over the place. It's not just one wave, it's like a collection of waves that sometimes constructively interfere and destructively interfere. So it's all kinds of values. One of my quantum mechanics instructors said, the only thing that we can see in quantum mechanics is the normalization of its coefficient. Basically, we can only see the produced result, called the observable. We can't see everything. We can't see everything that wave function includes, but we can see one discrete value based on the operation on that particular eigenfunction or function. So that's what I want to introduce you to down the line when we get there. But again, in classical mechanics, like you've had this year, everything is, I got this state, I see this state, done. Okay, done. I observed it. That's cool. But in quantum mechanics, you may have heard this already. If you don't look at something, then it's all the states, and you look at it in a particular state, that's what it is. You've collapsed the wave function. Now you're seeing the object at that particular moment, and it has that particular position, but you don't know its momentum. Okay, so they, which is another thing. The reason why you don't know its position and its momentum is because they don't commute. Position and momentum don't commute. That means they don't equal to 0, which means they don't have the same values as other operators will. That's the mathematical way of basically saying I can't know where the particle is and how fast it's going. There's no way to simultaneously figure that out. The derivation of that, quite interesting. It's quite cool. You know, dealing with integration by parts in order to get the uncertainty between position and momentum, which, you know, you probably have heard of it, the uncertainty principle, developed by Werner Heisenberg, 1921, where a bunch of guys working on the quantum mechanics. It's pretty cool. You got your Heisenberg, you got your Louis de Broglie. Even Einstein got in there a little bit. He had, you know, he won a Nobel Prize for the photoelectric effect, basically shine light of a particular frequency onto a piece of metal, and that photon of that particular frequency is going to hit an electron of it, you know, at that particular frequency, and it's going to bounce off and then produce electricity, you know. But it's not how bright the light is, it's just how it's the light that comes in at a particular frequency that's going to hit that particular electron, and that's going to produce electricity, blah, 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 blah. But he didn't like the whole formulation of wave functions. What do you mean? You know, you have this wave function that's a collection of everything, and then you have to do something to see what exactly it is. He didn't like that. But when you think of what a wave is, it kind of fits. It is what it is. Okay, so I love to ramble. Okay, so but like I said, y is the value or the eigenvalue. Value, eigenvalue. 2 in this case is the operator. X is your function. And that's what I say. Write the stuff down and go over it and speak again. Okay, so y the value, eigenvalue, 2 the operator, x the function, eigenfunction. Eigen, I think German means own or distinct, like that. You can look that up if you're curious. I don't care. It's something like that. Eigen, own. So these discrete values and functions just describe the state of a function. I don't like that. Thinking of something else, but I'll just say this. More intuitively, conceptually, visually, I like to think this is these values and functions describe the state of a system. Again, Schrodinger's cat. I'm not looking in the box. I open the box, he's alive. Do something else, he's dead. Some sort of operation happened. Either oxygen was pumped in there, or already there, he's alive. Poison pumped in there, the operator on the function, okay, now he's dead. But quantum mechanics, going back to the idea of superposition, when I don't look in the box, he's both alive and dead. Yeah, strange, but you can appreciate it once you appreciate what a wave is. A wave is not always one hump or 2 humps or whatever. It can be a number of humps. A microwave is not the same as a gamma ray wave because the frequencies are different. They have too many humps, and there's some over here, visible light. Waves they don't follow convention, meaning that they're not one, they're not separate unto themselves. That's why the electromagnetic spectrum is a superposition of all wave states, right? You have the TV, you have radio, you have the microwave, you have the visible, so it's a superposition. It's part of the same spectrum. So you can think of the electromagnetic spectrum as psi, as the collection of everything. But when you look at, you know, a particular band or area of that spectrum, oh, that's a radio wave. Oh, that's a gamma ray. Those are the values. What was the operation? Your sight. So again, it helps you get some understanding, some appreciation of what this is all about. These discrete values and functions just describe the state of a system That gives you a particular value. Different eigenfunction states yield different eigenvalues. So here's an example of discrete states. Like I said before, if you have a particle, you know, we've seen this already, you know, this year energy. So you have a particle, 2 kilograms here, and let's say it moves one time at 2 meters per second, 3 meters per second, 4 meters per second. You can observe at a particular time frame, a particular moment, oh, that the energy is going to be 4 joules, 9 joules, or 16 joules. We have 4 to 8, 9, 18, 9, 16. Yeah. Okay, right? So you can appreciate that. You were appreciating this without understanding, okay, at that particular time, I get this particular value. I observe 4 joules. Oh, 3 meters per second. I observe 9 joules. At another state, I observe 16. But understand one thing, they are not like waves. These are like state functions. I like to think of them as like this energy is like a function of position, even though it's moving here. But when you see it at a particular time, that's position. When you observe that ball in that fraction of a second, you know the position of it. You don't know how fast it was moving. Now it was tall too, but you can't see motion and position simultaneously. See? Right there, you were doing quantum mechanics without knowing you're doing quantum mechanics. When you're looking at your lab results or looking at the state of a system, right there, you're collapsing, quote unquote, collapsing wave functions for all the possibilities that could exist for that particular ball. Maybe it can exist in near or an infinite number of velocities. It's possible, depends on how you roll it. But when you watch that ball at that speed, that's that value. Operated on by the mass, because you know kinetic energy does not equal velocity, it is a function of velocity. Just like before, we were taking a look at y equals x. No, it doesn't. 4 is 2. Y is a function of x, but it's not equal to x. So again, this thing of quantum mechanics was seeped into your learning process even without you understanding it. We know that that's true, but in order for y to equal x, some kind of operation must, in order for this to be an equality, some sort of operation must be performed. Y equals the function of x is not the same as it equals. You know that already, but it's very proper to gain that rich understanding of it so you can do quantum mechanics properly and with precision. Okay, so here we go. Here's an example of discrete state. So there's our energy values. So like I said, in quantum mechanics, we deal with real functions and real values all the time. The reason why I said that is because we know that the velocity is not a function per se. You can get a velocity function. We've seen that before. X is a function of time. It's some weird quadratic, take a derivative of it. Those are functions, but you get the idea. But in quantum mechanics, we're always dealing with these cool things. We're always dealing with functions. Because remember, we are always going to be dealing with, you can say subatomic particles, you can say very small particles that have discrete wave-like properties. Like I said before, the electron, the photon, the proton, small little guys, because we can measure the observables better than we can looking at a matter wave of your computer. Yes, everything's made of waves. That's what this basically gets to, but we can't see the particular wave states of large objects. So that's where the realm of classical mechanics dominates, which we've done this year. Quantum mechanics, well, we're going to look at this electron and say, well, we just can't know where it is. I'll be saying this in a moment, but a particular experiment, you had an electron gun, and you shine an electron gun through two slits, you know, like a piece of cardboard, and cut two vertical holes in it. What was strange is that we know that the electron is a particle, but it was exhibiting wave-like interference patterns. Right there off the bat, you know that this electron is both a particle and a wave, just by observation. Now, we would have to do something to all of those different states to get one particular wave. In mathematics, it's called normalization. But we know off the bat that there is so much to this electron, so much to the photon, the proton. And that's also too why the focus of quantum mechanics is the hydrogen atom. It's the simplest atom where we can extremize, or we can map the results of the hydrogen atom onto other atoms. Very difficult to do without a computer, but we get a formulation of quantum mechanics. We can see the results of quantum mechanics quite nicely with the hydrogen atom. So that's why the hydrogen atom is a focus, because we have one little guy, proton, one little electron. Let's deal with it. You know? Let's have this electron go back and forth in a box, and okay, we know there's both a particle and a wave. We can get different states and different energies. I ramble. Okay, so you've come to this point and you've taken these notes. More special, crazy stuff to happen. So this is cool. I mean, quantum mechanics is very nice as long as you appreciate the wave. You appreciate that the wave is made up of many forms. Okay, and then from there you will know why you have to do something called normalization to get a particular value. You will know why that there's different energies, because the wave is in different forms. You're going to get different energies. And you have a particular operator that's going to produce those different energies and those different frequencies and other stuff, right? Different waves. So I'm fired up. I hope you are. All right, so let's go on to our next slide here. Let's say that we have a boundary. Now, I am very tempted to go and talk about the infinite square well, but I'm not gonna hurt you like that, because we can get a little wild and crazy here. But I will. Let me see. Stupid eraser there. Oh man. Trying to get rid of that thing. But anyway, let me extend this. And I will have another wave like that. Okay. You know how potential energy, gravitational potential energy, is a function of height? This is the same thing, except that this level here is a different energy than the one down below. So they have different potentials. There's something in quantum mechanics called the infinite square well. I remember the first time I saw it, I didn't know what the heck it was. I had no idea what the heck that was, but I just liked it because it just looked cool, looked fascinating. You know, I understand it today, but it was just, what is that thing? Why are you putting these waves and these particles down this freaking hole, this infinite square well? But anyway, it's just another way to represent potential energy on the quantum mechanical level. That's just a very fastball down the plate explanation. There's more to that, but yeah, basically what's going on. So if, say for example, this whole thing with quantum tunneling, just gonna as an aside, if the wave does not exist, say here, and let's say that the barrier stopped, like above this point, it was open space. If the wave didn't exist here, then, you know, obviously if the wave exists here, it can move, you know, but if the wave exists here, then the only way that it can get out of this box is to tunnel. And, you know, it takes this particular amount of energy to do that. Again, that's going way off the introduction. Quantum tunneling is a little too abstract for an introduction. But anyway, let me erase this here. I have to resist my temptations of looking at wells and stuff like that. Anyway, this is a particular wave that we say psi. Well, we're going to say psi 1. And then this is psi 2, and then this is psi 3. Already, those are 3 particular states of a superposed wave state we call psi. Usually with these little guys, we just we denote them by we denote them by little psi like that. All right. Because these are the particular states that make up the superstate of psi. Isn't that cool? Okay, so psi 1, psi 2, and psi 3. So all of those states exist between 0 and A, where the length of this box is A. Those are what we call boundary conditions. And the solutions of this wave function can only satisfy the boundary conditions for one particular type of function. For example, if I get a solution, and we've seen this already, if you recall, the solution, let's say, is going to be, let's say, psi naught cosine kx plus psi naught sine kx. Well, only one of these functions would, if we were to take it down that road, and we're not going to, only one of those functions satisfies these boundary conditions. And the only one that does is the sine function, because the cosine function at 0 equals 1. We want to get the solution such that the wave function dies at 0. And the only one that does that is sine. The sine of 0 is 0. So that's basically the long and short of that. Again, I would be very detailed in showing you that, but that's out of the scope. Anyway, so those are 2 particular solutions of this wave function. And all of these little guys have this form. Okay, so it's a superposition of cosines and sines, because we understand that all of those states can be sine-like or cosine-like, you know, all that good stuff. But the function that satisfies these boundary conditions is sine. And yeah, so because the only one that dies at 0 is sine. Why are we trying to have it die at 0? Because if it doesn't die at 0, then it continues, or it's an invalid solution because cosine of 0 is 1. That's 0. We have to get sine. So that's, again, like my summary of everything. I tend to keep the minutia of that. I can get to that minutia, but not necessary. But I'm gonna ramble anyway. I'll try to get back on the point. So again, all right. So we have these 3 wave states: psi 1, psi 2, and psi 3. Superposition to make the big guy psi. And we can do something called normalization to get either one of those. Which one is the most probable? Again, I'm not going to do that in this intro. So again, these are 3 eigenstates or eigenfunctions. Okay, got that? But an operator operating on these eigenfunctions will give me a particular eigenvalue, a particular eigenfrequency, eigenenergy, eigenwavelength, Just depends. So if I can indulge you for a second. So we have this well that can it be this, it can be this, can be this. So these together make up psi. Okay, superposition of three possibilities. But a particular mathematical operation called normalization will give me one of those. Based on that, I know the energy of that wave because I've done what is called normalize the wave function. But I'll leave that alone. Okay, so these are three eigenfunctions of a wave. We know that this wave in this box from 0 to A so exists or can exist in three discrete energies, frequencies, wavelengths, you name it, huh? You know, it can have a standing wave, so yeah, momentum, yeah, you know, it can do that, but you know, I'm not gonna get all caught up with that for the moment because you know, you're normally talking about a particle in motion, but yeah, we can get the three discrete states. Like I said before, in quantum mechanics, everything is quantized or discrete, right? So it has a distinct value. We can get a distinct value from a superposition of infinite number of values or near infinite. Get the idea, it's like a collection. So that's about it. All right. So, okay. Now back to operators. You do all this before I get to the derivation of that function on the APC page. A little reflexive. Okay, so now back to operators. Okay. In classical mechanics, what you studied this year, classical physics, we know that total energy of a system, okay, is the sum of its kinetic energy, and the symbol for potential energy is equal to the total energy E. And this is for particles, point masses, or even distribution of point masses, moments of inertia, and all that. So classical physics. Okay, so we also know that, let's call this equation 1, E equals V squared is not true, right? We had the example before, Y equals X, when they're both different values, it's not true. We can make them true by a particular operation. An operator has to be performed on the function to get that value. So it's invalid, especially if E is equal to 200 joules, let's say, and V squared is equal to 10. You know the one that's unequal. Like I said before, much like y equals x is valid. So again, take these notes down or just listen in. I'll be getting to the point eventually, but I have to take you down the path in order to get to the final result. You have to appreciate. I can't just take that function and start deriving it. Like, what's this h all about? Or what's this IH bar? And you need to know those things. And what's cool in quantum mechanics, the way you represent momentum is the imaginary number I times h bar times times a del operator. Don't worry about it. It's just that's part of the weirdness of quantum mechanics, but you can derive it, and But I will get to that in a minute. So this is invalid. I equals 4 equals 2. We got it. Okay. So in order to make equation 1 valid, we need something. Need something to operate on v squared to make 1 valid. So you may guess what the operator is going to be. Let's introduce the operator of 1/2 times m plus m over v squared gh. Random, it's some Hermitian operator. Again, that's just a term that you're going to have to travel down the path and do your own Google search on that if you're really interested on how Hermitian operators work. Hermitian operators are part of the linear algebra lexicon. Basically, the values of a Hermitian operator, the orthonormal basis of a Hermitian operator are the same in either direction. Again, that's a sledgehammer explanation, but again, we don't have to worry about commutators and Hermitian operators and things of this nature. Okay, this is our operator that's going to allow us to make equation 1 valid. So let's keep it as simple as that. Therefore, E equals E squared. Okay, that's what we started off. Multiplied by the operator, just like we had 2 times x gives me y, right? 1/2 m plus m over v squared gh. Looks familiar, doesn't it? Okay, that's kinetic energy plus potential. But we can only get there to make this 200 by an operator. Okay, so 10 times whatever this is gives me 200. 20. Okay. So obviously the velocity square root of 10, whatever that is, 3 point something. See? Now we're talking, right? It's not that this is the operator in classical physics. It's just in terms of explaining what the quantum mechanical operators and functions and values are all about. So now we're talking. This looks familiar, right? So again, to summarize, stage where I really want to get ahead and start doing an ordinary differential equation, but let's pause for you. Okay, so the function is v squared, and the operator is 1/2 m plus m over v squared h. That produces the value of E. Again, we can think eigenfunction, operator, or eigenvalue. That makes more sense when we have wave functions that are collections of eigenvalues, okay, or yeah, can produce different eigenvalues for a particular state of that wave, which is your eigenfunction. So if you got a wave with one hump, it's going to have only one type of energy, one with two humps, another type of energy. The more frequent it is, the more energy it has. So therefore, so you can kind of get more of appreciation for the other picture of those waves, because the more frequency gives me the more energy. I don't know if I introduced this equation or not. This is Mr. Max Planck, who's known as the godfather of quantum mechanics. In 1900, he theorized this formula for quantized energy states that would explain black body radiation. So basically, the more humps that you have in your wave, the more frequent, the more energy it has. So again, that's pretty much like a really simple way of understanding quantum mechanics basics. Then a lot of quantum mechanics really is some dense mathematical operations to get eigenfunctions and eigenvalues, things of that nature. Okay, so let's continue. So again, E, classical physics, is a function of V, or you can say V squared if you wish, the function of that, but it's not equal to V squared. It's like a function of X, but not equal to X, and so on. Okay. So it's a state or position-based value. This is a state value based on, I gave it something to the system. I rolled this ball at 2 meters per second, so therefore it can only have one energy. Let's say there's no friction, of course. Closed system, conservation of energy. 2 meters per second, 2 meters per second, 2 meters per second, 2 meters per second. I'm always going to get 200, 200, 200. Okay? I roll it faster. I introduce more of a variable in there. But like I said before, that ball cannot always, it doesn't have all the possibilities that it can roll in. It doesn't have all of the speeds. I have to introduce something to the system. Also, a ball at rest doesn't intrinsically have all possible velocities that it can ever have. I mean, but waves, they do, because of their nature. They, have waves that alternately constructively interfere, destructively interfere, based on a particular perturbation from the outside. That wave could have like 50 humps, and another one could have 5. It could have 3. So there's a large wave that can have all of those different states based on the interference patterns that this waveform creates. So it's not a state system, it's a collection, whereas velocity is just a state. I can't, that ball can't simultaneously have everything that it can possibly have. I have to do something to the system. That's really what makes classical mechanics easy, because you're only going to observe one thing at one time for one thing. Quantum mechanics, not so much. No, not so fast. Be careful with things. You can get as many possibles as you can, and even though you get as many possibles, now you get to the thing of probable. It will probably be in this energy state versus these other 10. So that's why quantum mechanics deals with probability. There's because of the possibilities. Which of these possibilities will this wave exist most probably in? And in this most probable state, it'll have this most probable energy, most probable velocity, probable frequency. So there you have it. It's funny, keep repeating that because you need to understand why quantum mechanics is so weird, because it's like everything and one thing simultaneously. Yeah, wrap your head around that. So little funky, little funky. In quantum mechanics, things get, as I said, a little funky. Weird. But there's like order to that chaos. Not really chaotic. It's just weird because our intuition mostly is geared to seeing one thing at one time, because most of us don't see quantum mechanics. And when we get to quantum mechanics, like I did for the first time, yeah, okay, so weirdness everywhere. And most of the class got weird grades the first time too. Weird, yeah, very weird. And once we started understanding it, we improved ourselves, all that stuff. Oh, yeah, that is, boy. The professor that I had at Cal, last time I randomly ran across some internet. He's now teaching at Cornell. I was following somebody on Twitter, and I looked at her profile, and she like works in the lab at Cornell, and I saw the professors there. Oh, Professor McEwen. Oh boy, random. Okay. Um, so anyway, great place. Okay, so in quantum mechanics, things get a little funky because, see, we deal with smaller particles. These smaller particles just don't behave, okay? You got an electron, you can't throw an electron to the wall. It might get to the wall, or it might go to the left, or it might go up. When you threw it to the wall, you just don't know. Based on the state of that electron, it's going to be most probably going to the left. Okay, so it gets funky down there. Deal with smaller particles. And that's actually kind of cool. It's actually easier. It's actually better because you know that you're going to get particular discrete wave-like values. You need to deal with smaller particles. It's like helpful and it's weird. There you go. These smaller particles have very distinct or discrete. My notes here, I wrote observable. So that, crap. Very observable wave-like properties. Like I said before, when you see something, experiment's over. The wave function's dead. The rest of it. Now, the question is, this is where we get into the whole concept of entanglement and what's this, quantum tunneling and what I want to say, or many world theory. So to us, the wave function dies. Sure, it's gone. But is it non-existent? Can another observable in that entire wave function exist, say, in a parallel dimension? That's where we get into all that kind of talk. So, yeah, and travel down that rabbit hole. I mean, at least mathematically, intuitively, it makes sense mathematically. Yeah, I mean, but anybody seen simultaneous, like, Rick and Morty does nice takes on that. So I'm not gonna talk about all that, but it's too far off tangent, but yeah, they're exploring that very fascinating idea that I'm looking at my screen now, but in parallel dimension, I could be standing up, or and to me, it's very weird because, and I think would be weird to you because like you're know where you are as you, and then another you is doing something totally different based on uh, the splintering, if you will, of the wave function. Weird, I just like the rest of the wave function goes someplace else. So yeah, it's fascinating, but that's what we in physics do. We play with toys. So, but there's some reasonability. I'll say that reasonability to it. So we say that particles can be both particles and waves. Lewis de Broglie, it's been, like I said before in that example, shine an electron gun through a double slit and see what you get. You're not going to get two electrons or one electron that just went, oop, right? I'm shining it through one slit, okay? I'm not going to see one electron on that sheet, on that screen. I'm going to see a superposition of waves. That is just like, this is way up out of here. That's just weird, right? So where does I have a focused gun going to a double slit apparatus, and I see waves. Like it's that proves a particle can be both a particle and a wave. It gets hit by a photon and goes off, and it becomes current. That's a particle nature. Shining electron gun through a double slit, wave nature. So we're going to get into the whole thing, Lamb shift coming down from classical mechanics to quantum mechanics, and do all that, but it is what it is. Okay, so be the same thing. So we say that particles can be or act, can be both particles and waves. Let me see if I remember the one de Broglie equation. May have this off, but one of his equations is P is H over lambda, where H is Planck's constant. So basically, it's different than the Planck limit because the Planck limit is the smallest length that you can get down to in quantum space. The whole Ant-Man movie. Man, crazy. Cool physics in there. But yeah, H is. I like to think of H, Planck's constant, as the constant that exists on the quantum level, or very small particles, or if particles that are less than or equal to the wavelength of light. This just a constant for small little guys down there, right? So we know that P for momentum deals with particles, and lambda deals with waves. So one of he had like 2 or 3 very nicely derived equations that were part of his PhD thesis. And not only did he get a PhD, he got a Nobel Prize. So good year for him. If you ever get a chance, look up the conference in 1927. All these big guys, man, the big wigs of physics in no time. I used to have that picture. I had to download it, man. All the big wigs, man. All the homies were in that picture. All the homies, man. You had Einstein, you had Niels Bohr, you had Paul Debye, you had Louis Broglie, you had Max Planck, you had Erwin Schrodinger, you had all the big guys in there. They had the Marie Curie, the only lady there. And no social justice warrior action happening in those days. They just, hey, she was invited to the party. She bossed out like that, okay? She just discovered radium. I think her hair was starting to fall out at the time, but yeah, she was there, and Max Born. I mean, yeah, all the big wigs. Einstein chilling in the front. He was starting to gray out, right, in 1927. He was in his happy zone because he had already published the general theory of relativity in 1915. So he was 12 years into his professorship, I think at Princeton, you know. But he would go back and forth with Niels Bohr, like, no, I don't believe in this quantum crap. And him and Niels Bohr would have all these debates, you know. Pretty cool stuff. They respected each other, you know, all of them, you know, obviously they, you know, Einstein just couldn't get down with this quantum stuff, right? Just trying to think of some other guys who were there. Okay, so we can say that particles can act like particles and waves on that quantum level. I just mentioned this, like, oh, crap. Okay, so double slit experiment. You can look this up, something like that. I mentioned that in a famous experiment, you shine an electron, then you got these electrons coming out in the stream, right? They're emitted from the gun. Come on, pin through a double slit. So if you ever look up, you know, Young's double slit experiment, just shining light, and you know, people understand that by this time, 1802, light is a wave, an electromagnetic wave. I'm not sure if they knew it was electromagnetic. I think that came with, that came later on in the 1800s with James Clerk Maxwell, basically confirming what Michael Faraday had theorized in the 1850s, I would say. He theorized that light is an electromagnetic wave, but he didn't have the math background to prove that. Because Michael Faraday, as brilliant as he was, as great as he was, coming up with Faraday's law of induction, where you can create electricity by having a changing magnetic field, which Tesla, like, I'm sure he jumped all over that, was like, right you are, Faraday. I'm going to take that to the nth degree. That's why we got cell phones today. So we have thinking about the length of this video. So it is what it is. Hope you're having fun out there. So Faraday, yeah, he theorized that light is an electromagnetic wave with 4 equations. Mr. Maxwell in the 1880s proved it. He had 4 equations of electromagnetic induction. An induction equation. He had a one that's called displacement current. Remember all of them. The cross product of E giving me magnetic field as a function of time. This is just, you know, four equations to verify that. Not only did James Clerk Maxwell show that light is an electromagnetic wave, but he proved that the change between an electric and magnetic field happens at the speed of light. His equations showed that. So that was landmark. So this is the late 1880s or the 1880s. Now see, Einstein's going to university around 1900, 1896. Fascinated with that result. He gets into the Swiss Institute, physics or science or whatever it was, and he's thinking about light all the time and what happens if I go at the speed of light. I mean, what did it? and all that nice stuff, and then he just comes upon his special theory of relativity and his general theory of relativity of light, and, and so on. Man, this is great. And then it's simultaneous with Einstein thinking about light. Time he graduated from university, Max Planck, as mentioned before, the guy who came up with this, derived this formula. Quantum mechanics was getting started. Now, Einstein was over here, and quantum mechanics over there. They converged about, in the 1910s somewhere, when Einstein took the principle of Max Planck and said, okay, shine light at a particular frequency, I'm going to get a particular electron. I'm going to get electrons to fly off this metal. And, attach a wire to it, and you got electricity, a voltmeter, and got electric current there, or ammeter. So there you have it. But back to this point, double slit experiment, electrons emitted from a gun through a double slit. And they hit the screen like a wave. Like that. Never mind. Okay, I just know it's like, what? Like they hit the screen like a wave? What? What's going on here? Told you this down there, man. It's weird down there, man. Let you know. But I won't travel this hole any further because we'll be like Alice in Wonderland. So I want to get back to the focus, because that's a rabbit hole that this video might be like 5 hours. But I'm not gonna do all that. Well, with me rambling, it might be 5 hours anyway. But 5 hours anyway. So yeah, let's continue. You're having fun out there, as much fun as I'm having out here. Over here. It's just so cool. I hope you can understand. Okay, we got a function, an operator operating on that function to produce a value. Okay, hope you got that in mind. Keep that in mind, because we're going to get down to the nitty of the gritty here. In quantum mechanics, we handle particles that, like the electron, the photon too, give the neutron some love too. Like the electron, by their wave-like behavior. It's like, neutron has no charge. This is not, it's fun at the parties. He's necessary. Wouldn't have any glue for the atoms here. Wouldn't have the strong force to hold the nucleus together. So in quantum mechanics, we handle particles like the electron by their wave-like nature. So this is what we're going to have to do. We're going to have to transform our classical mechanics energy equation into the quantum mechanical equivalent, which you will see as the Schrodinger equation. There's a very heuristic way of deriving the Schrodinger equation. I'm not going to do that because that's going to extend and take us off the level. But I'm going to just show you the Schrodinger equation, and from that, I'm going to then derive the equation that you see on the front page of AP Physics C. And I'll stop the video, and then I'll be creating the angular momentum video for Friday, because I know I'm at least an hour in, but we're having some fun. Okay, so in quantum mechanics, we have particles like the electron by their wave-like behavior. Therefore, we need to go from particle to wave. Look at that. Telling you, that's all it really is. Of course, when you look at the electron, if you see the electron on scanning electron microscope, if you could see its shape, it doesn't really have a shape in terms of round. I may be in error in stating this, but I don't think people have actually seen the electron in its a round little dealio that hanging down there. It's a cloud. There's registration for the electron, meaning that there's manifestation of its properties um, uh, based on the operation of its wave nature. You can see the evidence of it. That's why I was looking for the evidence. But if you could see the electron, okay, that's classical physics. Okay, I got a nice little ball here. But in quantum, it's all waves, even waves. So it's both, but quantum, we deal mostly with its wave-like properties. That's pretty much what's going on. But we have, and when we do that, we have to be careful. And we'll practice it. It's nothing. Yeah, the basic level is nothing. You start getting into ladder operators and climbing the ladder of energy, quantum mechanics. There's obviously some advanced, very grimy aspects, but the intro, once you get that, you can take it and reconceptualize on the advanced level, because you're still dealing with waves. There's many manipulations, and the equations get complex, especially when you now deal with like an electron, for example, a spherical shape. We're going to assume spherical symmetry. So we can't deal with regular X, Y, and Z coordinates. We have to deal with spherical coordinates, and that's where the Schrodinger equation gets really funky. And then we have to do something called separation of variables to get the way that an electron has precession, it has rotation, and then it also has a particular radius. And that's pretty much, I know I'm rambling again, but that's pretty much how you get your, the spherical coordinates, for example, are radius, rotation angle theta, and precession angle phi. So that basically means those are the three particular states that an object of spherical symmetry can exist in. Once you spin it, it can spin, rotate, of course, and then it precesses about its z-axis, if you will, and then it has a particular radius. Spherical symmetry, spherical coordinates. And I will, in my ramble, I will, in the next video, I will be showing you what spherical symmetry looks like, because that's very important in appreciating the angular momentum operator. Like I talked about operators, well, in just a few moments, I'm going to give you what is the quantum mechanical energy operator, which is called the Hamiltonian. There's all kinds of operators hanging out in quantum mechanics space. It's a Hamiltonian operator, it's an angular momentum operator. I mean, everything's an operator pretty much. You have a force operator. I mean, because you're talking about something that's going to operate on a wave function, an eigenfunction, to produce an eigenvalue. There's acceleration operators. Everything down on that level is an operator. And it has particular significance when we're talking about matrices, because these operators can be spliced apart and to form a matrix. And that operator matrix can operate on different states, different wave states, to produce different eigenvalues or eigenstates. for the same wave function. So the merge of uh, linear algebra, which again, please master that. Yeah, it's going to give you go a long way. Linear algebra on your college level. Once you have that, you can really appreciate and understand quantum mechanics in a deep way, deep level. Yeah. So there's that. Like I said, so we will transform from E equals K plus Q. We know that's total energy, right? Classical mechanics, where we have E is equal to V squared. And I just introduced an arbitrary operator because I was saying if I have a function of V, this will be my operator. If I had a function of M, then I would have to, that 1/2 M plus M over V squared GH. Okay, so again, this is my operator. This is my function. And this is my value. Eigenfunction, eigenvalue. But we know in this state, it's really just a static function and a static value because we're only going to get one of each for whatever we introduce. But a wave, it introduces itself, right? And so we're at the mercy of observing where it is. So that's why there's eigenfunctions, eigenvalues, because a wave is many things. Okay, so that's the state energy operation there. And so now in quantum mechanics, we go from, the energy in quantum mechanics is going to be equal to a function we just mentioned, a wave function times an operator we call the Hamiltonian. H hat, okay, operators in quantum mechanics space has this hat business to it. Just mathematical symbology. Okay, let me see if I can. Yeah, so H hat is for Hamiltonian. It is Hermitian. Don't worry about it, the Hermitian operation. Hamiltonian is basically the operator on this wave function psi that produces these eigenvalue energy states. But written as is, let's say H psi equals to E. When you write it like that, that's a state function. It's like, oh, well, I get one particular function. I can introduce a wave. I can introduce like psi. Like if you wrote it like this, you're basically saying that psi can only be one value, 2 meters per second, or 2 something, 3 something, 4 something, and I have an operator, the Hamiltonian, to produce E. But again, as mentioned, I said, the psi function is a superposition of many states. So the energy that you're going to get is going to be a result, is going to be not a function of the wave functions, but it's going to be a result of them. So technically, okay, we need to write this equation as H hat psi equals E psi. Now, again, that has particular significance and value for linear algebra because this equation here is what is known as an eigenvalue equation. And that basically says that you can get, when you put all the values in a matrix, for example, you can do some nice little operation on it to get the particular eigenvalues. But as is, in terms of the wave function, let me just give it to you even simpler than that. Since the wave function is many little small functions, the energies that you're going to get are going to be in terms of That's functions of, but in terms of the different eigenstates. So you can have, you're not going to get just one value because psi is not just one, it's many. So the energies are going to be of many forms. This is basically, it's an eigenvalue equation, but it's like also a energy superposition equation. So you can get all these different types of energies from the operation of this Hamiltonian on psi. Okay, so but again, that is a bunch of verbiage. You don't have to worry about it. Obviously, I just want you to get some appreciation. Okay, so this operator H on psi produces E psi. Now, if I said something about normalization before, normalization is just an integral of all the wave states, and I can get a particular eigenstate or eigenvalue. Since I've been talking about it, basically when you normalize, let's say we have you have a wave function psi, and then I like to think of it this way. Okay, it's not, and I don't care if it's just not the standard way. Okay, here's the deal. When you normalize this eigenvalue equation, you're taking the wave psi, doesn't matter how many states it's in, we're going to solve for what psi is actually going to be. And you multiply it by the complex conjugate. In other words, let's say you have this wave that's moving to the right. Its complex conjugate will be moving to the left. The superposition of those is going to give me energy because the integral is going to be like opposite exponential functions, and that's going to come out to just be 1, right? So in quantum mechanical nomenclature, it's psi star psi is equal to psi star h hat psi. You don't even need to worry about all that, but what I just did there is to show you that when you normalize on this operator, you're going to get all of these energy values. That's really what it is. It's a nice fancy mathematical normalization type deal. You may have seen it before, but you will. But it's just this. It's like, okay, I normalized this wave function, and based on this operator doesn't change. Based on what these psi's are, I'm going to get different e's, right? So like if I, like it goes back to the kinetic energy example. If I put in 2 meters per second, I push it, then we get 4, 16, 9, all that. Same thing, same concept with the wave function. I normalize it. If it's a particular state, I normalize that state. This is called normalization. When I normalize it on both sides, I got to do, both sides of the equation. When I normalize, I'm going to get these e's. E1, E2, E3, da-da-da, da-da-da, da-da-da. And typically, this form on the right is a matrix. And I can put these values into a matrix, and the values along the diagonal of the matrix are basically the different states that this wave can exist in to produce these different energy values. Again, there's a lot. Don't worry about it. Again, we're getting closer to the derivation of that equation on the APC page. Okay, so this is cool though. I mean, I hope you had some. So this is a normalization. So the operator's there. This is a normalization about this operator to give me over here, because this comes out to be 1. And then when I integrate this is a fancy way of saying integrate. Whatever I produce from this operator through the integration, I'm going to get e's. Right? That's another way you can get values. There's another way you can get E values where you derive the equation for the energy states in their integer multiple forms, where n is equal to 1. I'm going to have energies 2 joules, and then 3, and then 4, and then 7, or whatever. And the thing with quantum mechanics, you will never be dealing with decimals. It's always discrete integer values. You will never get 7.5 of anything. It's just 100, 110. So what would that be? Like a whole number, no decimals. That's also the particular asset, the particular thing about quantum mechanics. It's always integers. So let me write this equation again. H hat psi equals E psi. This is the, now, okay, so I guess I'll just say, this is the time independent Schrodinger equation. The nice, happy way of deriving this. Remember going through the steps of that. Actually, I just found out that Schrodinger, he derived this equation, like he started it from like a heuristic mathematical, like he started off with a basic mathematical form, a mathematical function, some kind of unitary function he started off with. It's basically a typical mathematical idea where you have a function, right? So you have an operator that's going to be on some function that's going to produce a value, but it's like this is an abstract form, right? And so a couple of assumptions put into it. He derived his equation here. Well, yeah, this guy. Well, it's actually the time dependent equation he derived, and you can come back and do the time independent. It's very easy. And one quote by I saw this on Wikipedia. One quote from Richard Feynman. It's like, where did the Schrodinger equation come from? Nowhere. It came straight out of Schrodinger's mind. It meaning like there's kind of like no precedental basis for it, but it's like it's based on a basic math rule, but it's not like a result of something else that leads to this, right? It's like this is a position that it's like, okay, I'm gonna take what's going on with this wave, and I'm going to come up with an equation that can describe it in different states. Right? Anyway, that's a little anecdote on that. Okay, so let me get down to, all right, so Hamiltonian. So we said that the operator for regular energy is this 1/2 m plus m over v squared gh. I just made that up because, because the velocities, we just need something to act on that v squared to give my e. So, but the Hamiltonian, very specific, negative h bar squared over 2m del squared plus d. Okay, that's a plus sign. Again, cryptic symbology, don't need to worry about it, but I'll explain it. So the Hamiltonian, this is an operator on the wave function to give me my E values. H bar, this is the Planck's constant. So H bar is equal to H over 2 pi. 2 pi. 2m, m is mass, and del, this del operator, this is a derivative in all coordinate space, whether it's x, y, z, Cartesian coordinates, spherical coordinates, cylindrical coordinates, whatever space you're in, this operator, this del operator, is a derivative for. So we'll see when we get to angular momentum. Very cool. We will see that this del squared is an operator about del x. Okay, it's got a symbol for pin battery low. So I'm gonna hurry up here. Del y squared plus del z squared, partial derivative functions. Okay, if my pen dies, I'll resume. But anyway, again, we don't have to worry about that stuff. I'm not going to do all that. I'll take you to the steps for the angular momentum stuff. But like I said, this is regular Cartesian coordinates, x, y, z. You can transform these coordinates into spherical coordinates, where it's real funky 1 over r del r squared. But it gets it's pretty cool deriving it. Long freaking time, but it's nice. I did it once. I don't have to do it again, but it's pretty cool. Okay, so let's get back to the point here. So that's my Hamiltonian operator. So if I want to rewrite this equation up top now in terms of the full Hamiltonian action, psi, remember, okay, plus b psi equals e psi. Now again, this is h over 2 pi. This is basically Planck's constant, blah, 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 over mass of the electron. This is the del operator. This is the wave function. This is potential. This v here is potential energy. So you can think of this as k plus u equals. This is the way to represent total energy in a quantum mechanical system by way of the time dependent and time independent Schrodinger equation. Remember when I first saw this in spherical coordinates, I first saw this in spherical coordinates sophomore year in college. Didn't know what it was saying, but I just thought it was a cool expression. And I knew I was going to learn it pretty soon. So yeah, this is the time independent Schrodinger equation. Why time independent? There's no t terms, all right? But a wave exists in space and time, so there is a time dependent term. So let me get on to that one. I have a quarter left of energy here. So right. The next slide. So we just saw the time independent Schrodinger equation. Goes back to our first premise, operator, eigenfunction. I'm just going to call it wave function because we can get particular sets. The wave, it's not an eigenfunction yet because that's eigen means discrete. So I'm not going to do all that right here. But we know that this wave function is a combination or superposition of eigenfunctions. Okay, this is a wave function, or basically the function that we saw way in the beginning, y equals x. Okay, so wave function again. The energy is not going to be a static value. It's going to be a combination of everything, and then we can do normalization to get a discrete value. And this is my eigenvalues. In math, this is what's known as an eigenvalue equation. Okay, time independent Schrodinger equation. Now let's go on to the time dependent. So h psi on that opening page for physics C, I have this. So this is a time. This is energy. Okay, we're gonna prove that. So this is the time. This is the time dependent energy Schrodinger equation, and this also equals to E psi. Now I'm gonna prove that this here in the box is equal to E, which will give you more appreciation that, oh, this is just energy. And you just say, not necessarily conservation of energy, it's just that saying that the total energy is equal to h psi equals IH bar del psi over del T. This is the quantum mechanical way of saying total energy. All right? So I'm now going to prove that that's equal to energy. Now to prove this energy, first thing I want to do is Okay, one second. Okay, first I need to derive the wave function psi. I need to derive it because I need to get the possible values of this wave function in order to then show that the time-dependent Schrodinger equation is actually an energy expression, okay? I'm going to show that this is equal to energy. It is, but and another thing here, this is like the time derivative of momentum, and when you do that, you get work, as a matter of fact, which is an energy. Energy. So, all rather fascinating. Okay. Okay, let's. So what we want to do first is. Okay, am I still recording? Okay. Well, I'm going to take a break. I'm going to charge my pen here because he stopped writing on me. But I hope we had as much fun as I had so far. So this is really freaking cool because once you can appreciate that it's all waves and your linear algebra is very good, man, you're powerful. You can become a powerful quantum physicist. Down the line, you choose to. So let me stop here and come on back. Man, this is so cool. Talk to you later.